All right. We'll go ahead and get going. Sorry for the little delay. Some of you guys not quite ready to get going. How'd you feel about the exam? Some goods? Some thumbs up? Great. Glad to hear that. Any major complaints or don't want to talk about it? Or all right. Well, I have a lot of grading to do, this class and another class. So I won't have it to you this week. I'll next week. My internet's having a few issues here. Let me just go ahead and make sure I'm recording. And so I think my slides are current, but I'm not able to connect to OneDrive. So I think we're fine, but just a little warning if I have to stop for something. We'll get it fixed and cleared up, but I think we're good. Anyhow, you don't need to know about all that. Here we go. Today we're going to talk about granular filtration. We almost started this kind of at the end of last section. So for the next exam, we're going to do granular filtration, a bit of membrane filtration, and then some disinfection topics. That's the plan at the moment. So it'll be, whereas we began with primarily physical processes and kind of learning mass balances and just a refresher on chemistry, now we're going to get into a few more physical processes, but leaning towards chemical processes and applying the mass balances for, or mass conservation of mass principles for this type of thing. Again, with the physical processes, sometimes we'll have for filtration, not our typical mass balance in terms of like, we don't really have a reaction going on, but it will be conservation of mass. We are separating stuff in some manner. So there's two types of filters that I want to talk about. And if you ever hear about any sort of water treatment or filtration, it's often used in our common language very, very casually. We are filtering water, meaning we are doing something to it to treat it. But a filter specifically has more specific technical meaning. So we have two types of filtration then. One would be granular filtration that we're going to start talking about today, where we might have sort of packed bed of granules with water filtering through it. This would be very much like having groundwater that's flowing through the soil. Yeah.
So is this like a model of like that's water on top and then a solid that's settled after some time? Or?
So what I'm drawing here would be some sort of a bed filled with sand or some other granular material, and water is on top of it, meaning it's also inside of the sand. And the water, in this case, we would be filtering, maybe we're adding water here, and the water would filter through it and be collected. So in this particular scenario, we're calling this granular filtration because this is grains of sand or something like it that are allowing particles and other stuff to stick to it and be removed in that manner. So if this would be granular on this side. This is distinct from what we would call membrane filtration, which is acting like a screen. So if you think about it, you pour a bunch of water through the soil, well, the particles, you'll get some particle removal. You won't have as much stuff, as long as you're not kicking up the mud and making particles come out into the water. But if you extract groundwater or you pour water through some granular filter, we expect it to become a little cleaner. That's a little different, and it takes a lot more material to accomplish that compared to passing it through a screen, a membrane. And if you think about it, a screen will act as a physical barrier. So if we have a particle trying to go through, the water will go through, and then the particle will kind of get stuck on the surface. That's a physical size exclusion that's happening in general for membrane filtration. The important thing here is the granular, you can actually have a particle that's really small compared to the pore size between, and you bump into something. Well, if you're sticky, then you're now stuck to that wall. So even if you were able to navigate a little corridor, maybe you run into another particle and stick, and then you're too big together, or maybe you just bump into the wall and you get stuck. Okay, so that's kind of what's happening in the granular filtration case. A good example of this would be your Brita filter. We are not size excluding anything when you pass some water through your Brita filter. Or the little filter thing that's in your refrigerator that yells at you when it's been 6 months and they want you to buy a new one, right? What that physically will be a charcoal, essentially, activated carbon is what we call it, filter that has granules, and in that carbon material there's a large pore size for things to go in, and it happens to be pretty sticky for a lot of chemicals and particles. And it's actually the chemicals in that sense that the Brita filter or something like that does a good job with. So if there was a little bit of caffeine or something in your water or some other molecule, is a good chance a filter like that might be able to take it out. Now, that's just going to sit there. It's not excluding particles by size, but it might capture some. So that's kind of the analogy. You could also think of like a coffee filter where the filter itself is acting like a size exclusion, kind of like a membrane filter to hold all those coffee grinds. Now, to extend the analogy a little too far maybe, the coffee grounds themselves would be doing some sort of a granular filtration. It might catch some particles because it's water flowing through that granular media, but in that case, of course, you're wanting to discharge some chemicals from the coffee grounds so that you can have your brown water, right? So just kind of thinking about how in practice in life we might see this type of stuff. Another good example for the membrane is a screen porch, right? We want air to be able to pass through the screen, have a nice breeze, but we don't want those mosquitoes or other bugs, right? So we are filtering out certain sized objects, but allowing the liquid through. Okay, so that's going to be our membrane filtration compared to the granular. So today and next time we'll talk about granular filtration and what does it do, how do we do it, how do we design it, and what are the key operating principles that we need to keep in mind. So like I said, granular filtration, it's not necessarily size exclusion. Often cases it's not. Of course, sometimes it will be if you have a large particle meets a small pore. Okay, we can get mechanical screening, we could call it. We might also have sedimentation inside these little pore chambers. So legitimately just gravity acting on the particle and it settles out. Touches one of the other particles and we've got it. We could have flocculation where these little particles meet and now we have a larger particle that gets stuck. We could have interception where the particle is traveling along and it just happens to bump into the side of a wall because it didn't turn as fast as the water was turning. Right? It has a little bit more mass. It's carrying along and it just bumps into the side wall. Or maybe impaction, kind of like sedimentation. You know, whatever you want to call them, there's different phenomenon. Maybe we could do different math on each of them. My point is just simply that there are different ways in which the particle may get stuck because it bumps into the wall. So there's some fancy terms for that. But the neat thing then is you can, if you stop and think about it, you can recognize you can then dislodge and clean this filter, not a membrane, by reversing that in some manner. So if you took an aggressive backwards flow, perhaps shook these grains up a bit, maybe most or all of these particles can then be removed again now that you've caught them. So that becomes very convenient. Do you have a question? Or okay, yeah.
Is it really important that we know the differences between?
No. No, you don't need to know the differences. I'm just showing you that there are many different ways. And if you wanted to focus in and do research on granular filtration, maybe then you might want to know. I'm just showing you there's a few options. In practice, these things will take a variety of shapes. I've got a couple of videos to show you towards the end of class, just kind of what that backwashing process might look like. Gives you a good feel for what this whole process is about. I also have some granular filters that were donated to LSU in my lab, so if you ever were pretty curious and wanted to play around with it, let me know. Got a system there. And these would be pretty small ones. You know, maybe you could treat enough water for a couple homes or something like that. Normally, you might have something a bit larger, and oftentimes it's not even in a column. You can get higher pressure and a little higher flow rate if you pack it into a column. But normally, we just would lay it out on a bed if we have the space and let gravity pull the water through, and it actually turns out to be quite convenient to do it that way. So the granules themselves are actually fairly important. We want to design a system where we have pretty much the same size material. Sometimes we might have a couple of layers, maybe something like this activated carbon or anthracite, and then just sand, or maybe sand with some special coating, try to adsorb stuff better. At the end of the day, it's going to be a bunch of material loaded into a big bed like this, typically. And then as we flow water through it, we have some typical characteristic because we have a nice high-grade material that is typical in nature. And the great thing is we should be able to reuse it almost for eternity, right? It's just these granular materials. They're not really changing as we use the process. We're just going to be catching particles and then washing them by dislodging those particles and retrieving them in a waste stream. So these will be a very handy way to perform filtration and be able to do it for a long time. So you see the first scope. This is one of those granular filtration beds here. We'll see them often looking like this. The troughs here, this is typically how we would add water to the system to let it overflow into the bed and then be collected underneath. Or when we're backwashing, we'll be pushing water up from underneath, and then water will overtop into these troughs and we can collect it. So that's just typical. It doesn't really have to be done that way, but that lets you spread out the water across the bed and collect or distribute it from one kind of general area. So you see there's a person there working with this. I guess this is probably a 1 cubic meter of granular media or something like that. So these are going to be loaded up with quite a lot of media, and it'll be a large operation. And you can imagine if you have to take it down for maintenance, that's probably a pretty big task. Okay, here's a few in operation. They're all filled right now doing filtration for some treatment plant somewhere. Okay, so just a tiny bit of history here and a few terms that we're going to use. In modern day, we call it a rapid sand filter, and that comes from the history that we would have, the first media filtration would have been what we now call a slow sand filter, where we put water on a bunch of sand and let it slowly percolate through and allow whatever processes happen to allow essentially what happens in the ground, to kind of imitate groundwater and the natural treatment that groundwater receives. So this, perhaps the first time we'd ever done anything like that formally for like a municipal treatment would probably be the 1800s. And when we do it that slowly, we can actually have biological processes helping too. Helping or perhaps hurting depending on how we look at it. But if we had dirty water, microbes might be able to eat some of the junk that's in there and convert it to stuff that's just going to be left in that sand plus bacterial mass. Nowadays, we send water in much quicker. We're not waiting long enough for biology to happen. Of course, there's probably going to be microbes on the sand or the grains, but that's not anything that we are designing for or intending to use. Okay, and that would be like you put a bunch of water on there and then it probably stays on the sand for a couple days time for the slow sand filter. We're looking at the hydraulic retention time. So nowadays we're sending water in much faster. We're going to talk about some of the rates of loading water onto the filter and the rates of backwashing, things like that. So as we talk about the filter operation, we're going to talk about filter ripening. How many of you have ever filled up a new Brita filter thing of water? Do you use them? You ever have that experience where a bunch of little black specks come out into your water when you open up a new one? Anybody? Okay, some. So some of you have seen that. If you open a brand new one and use it without any flushing, there's probably a few particles that come out. That's actually kind of typical. That's just some fine, small particles of that media that just are loose and escaped. So you generally recommend allowing it to operate to flush some water through before you start doing stuff. That's exactly what we're talking about here. Let the particles get into kind of a stable arrangement. Any loose particles that were hanging out small enough to escape, let them go ahead and escape. You can imagine if you are washing and then reusing your media, you might have some dirty particles. So in the case of the Brita filter, hopefully it's all clean, so it wouldn't matter, but it looks gross. But if we had a dirty filter and then washed it, but there's still some of those dirt particles in it, now we really want to flush out whatever particles might be hanging around that can still escape. So the first few minutes, maybe 20 minutes of operation, we actually are producing wasted water because it's got those dirty particles. And hopefully it's not the sand itself, but in the case of the Brita filter, there were just some smaller chunks of carbon and they're just escaping. So this is that kind of a warm-up period. Maybe we can say we're letting things settle within the filter. Something like that. Next, we have the term backwashing. Kind of already introduced it. We are putting the system in reverse. We're taking clean water and flushing it backwards through the system. And by clean water, I mean water we've already filtered. We throw it through reverse. Maybe sometimes we will add some air into this process, as we'll see, to help shake up all the particles, to shake loose all the dirt. And then we are going to collect that dirty water and send all that to waste. And really, all of the math that we're going to talk about for this segment comes down to how are we managing how much water we're producing compared to wasting because we need to backwash. So it's almost all water management here in terms of, okay, we're producing this much with this many filters for this amount of time, but every 24 hours we have to take it off for an hour to do our backwashing process. It's going to use this much water, blah, blah, blah. So it's really, for granular filtration, that's the design key, is to manage, okay, we're producing this much, but we also have to use some of what we produced to backwash, to operate in this efficient manner. So it's going to waste some water, aka send it to a wastewater stream to be treated, but overall it's a very good process. It's cheap otherwise and reliable. So how do we know when we need to backwash? Well, there's a couple terms that we're going to talk about for that. One would be head loss, so loss of pressure because particles are becoming stuck in there. It requires more pressure to pass water through the filter. And then turbidity. Turbidity is a term we already talked about once. This is kind of a measure of how many particles are in the water, and it's a measurement we use by kind of visual or light scattering. So even in a bottle of water, right now my bottle of water here is not very turbid. You can see kind of directly through it. But if I make a lot of small bubbles, those bubbles are going to be, at least for a moment, causing some turbidity. They're scattering light. So if you've ever gotten water from a water fountain and there's like a million tiny, tiny little bubbles, it makes it look milky white. But if you let that water bottle sit there for 5 minutes, those bubbles will coalesce and be removed. I don't know what happens in the water system, maybe something funny with the filter. Sometimes it just comes out that way. But if you watch, they will kind of coalesce and disappear, come up to the top, and then it will be clear again. So that's turbidity, is what we're talking about when we see particles are scattering light. It doesn't really matter what kind of particle. My bubbles didn't stay very long, so it's no longer turbid. But while I'm shaking it, certainly there's a lot of light being scattered by the bubbles. So that's a measure of our particles. So we can monitor and say, okay, if we ever have a lot of particles escaping our filter, we know, hey, alert, it's time to stop. Because the filters will fill up, and eventually particles will start making their way out when we have too many. There are other things that can happen if we get too much pressure, because now it's harder for water to pass through. You end up adding more water on top. That's putting more pressure. Eventually, if we have too much pressure, we'll kind of just part the sand and water will just flood through with no treatment and carrying all the dirty particles that they just moved around with them. So we could have a big spike in dirtiness, turbidity, and we know, hey, emergency, we should have stopped sooner. So there's a few ways we can trigger this, okay, it's time to backwash. A better visual here for you for turbidity, looking at low turbidity on the left here, clear water, and highly turbid water over here. And you can see it's not necessarily the color, although this is sort of a brownish orange color. We can see from the particles, it could be milk, right? It could be white that's causing this turbidity. So it's not necessarily the dirty color. And in fact, if you operate these big granular filters from in one location, you would find a different color of sediment or particles in some other location. So where I grew up in Georgia, there's a lot of red clay. And so I imagine that if they're operating these, they're, from a surface water treatment system, they're probably going to look something like this, maybe even a little more orange. Here, it might be a little more brown. There's just not as much of that redness in the natural sediment. So kind of depends. But turbidity itself is that cloudiness, is my point. So a few ways to measure it. And basically, you're just kind of looking how far can you see through this water before you can no longer distinguish between this little Shecky disc thing is a common way to do it. Okay, so when we determine our backwash frequency, we're going to use some combination of that head loss, the turbidity, and sometimes maybe we'll just set it all as a time limit based on what we know, how long it is okay to operate these typically in a safe manner. Yeah?
You're talking about frequency, like how many times you would have to backwash to make efficient filtration continue?
Not how many times, but how often. Yeah, so frequency is like the frequency with which we have to take a filter offline to backwash it and to do that process to get it cleaning again. And if you think about the filter in your refrigerator, you don't have a lot of particulate matter there. You don't have a large flow rate. It's going to last a long time, and it's not actually removing anything that's too important anyway. So it's probably fine if you ignore it, unless your refrigerator decides that it's smarter than you somehow and tells you can't use it anymore. That's silly. But barring that kind of nonsense, you shouldn't have to have a very high frequency. Even if you wanted proper treatment, it's like once or twice a year at most, right? For these, it's going to be a lot faster. We've got a lot dirtier water, a lot higher flow rates, and just a lot more crucial stuff going on. So these are typically the time limits, typically between 24 to 96 or 100 hours. So that would be one backwashing cycle for every 1 to 4 days. So that would be typical. Now that's the time limit of operating the filter before you would need to backwash. So when we talk about this whole backwashing thing, I'm going to kind of draw a couple diagrams here. What I really want you to pay attention to is what's the total cycle look like? We're going to ripen first, then we're going to produce water, then we're going to stop, and then we're going to do some maintenance and backwash. Then we're going to start again, and we're going to start with ripening. So it's that life cycle or that filtration cycle. We kind of need to capture all of that to understand where the water is going. in order to design a system that can adequately treat water. The catch here is that we need enough filters to constantly produce water, even though sometimes we have to take them offline. And so when we design a treatment system, we have to keep in mind that at any given moment, we might have to take something off for routine maintenance, and maybe we should build in some capacity in case we have to do some unplanned maintenance. What happens if one filter has some plumbing problem that we just can't operate it anymore, but we still have to take some offline to do the backwashing, right? We have to kind of keep in mind as we design something like this, what in total, how are we meeting our flow continuously? Okay, so we've got the different methods: head loss limit, time limit, turbidity limit. Usually and ideally what we would do is have a convention. We're typically going to do this, but we're also monitoring the turbidity. In case a turbidity event happens, we know something's going wrong or we know we need to clean it, that should trigger something automatically. So this pretty much should be monitored regardless. Okay, so usually a combination of the first two and then also watching turbidity. I guess maybe you could conceive of somebody not doing that, but I think turbidity is always monitored. So let's take a look then. What would the turbidity look like if we are starting a new cycle? So like I told you before, the beginning is some ripening. This is sometimes you might call it rinsing. Since you can't read that handwriting there anyway, it's not very good. We're just going to say, I'll just redraw it. So ripening or rinsing for the first little bit right here. The turbidity will actually be kind of high. There's particles escaping because everything was just shaken up. Even though we backwashed it for a little while, there's still some particles kind of hanging out and not stuck and stable. So when we first start operating, the sand will be rearranging a little bit and we're going to get into a groove. But before then, we're going to have some turbidity, but it'll decrease up until the point where we're ready to operate. So essentially how long we rinse is about how long it takes before we have a low level of turbidity that's pretty much stable. So then we're going to do operation or filtration for some time. So for the next many hours, this is what we want to be a big number. We're just simply going to be doing filtration, or maybe we'll call it production. We're producing water up until we reach a spot where we can no longer filter. And if we have some cutoff where maybe I'll make a cutoff in a different color in a moment, but we can imagine that our turbidity will probably be fairly stable and then eventually start rising as we reach the point where we have to stop and backwash. So if we're defining it some sort of cutoff, let's say here, so some value that we know if we reach this spot, we must stop filtration. It's getting too dirty. Ideally, what we'll do is we'll have some end point where we're going to end filtration. Hopefully before we get that cutoff, right? Hopefully before we reach this kind of emergency setting. Now, if we reach that emergency setting, we should shut it off immediately, and that would trigger it. But something like a typical profile would look like this, where we say, here's where we're cutting it off. Turbidity is starting to increase. We know we have to wash this filter. So then we would have, perhaps if we're doing it, we would maybe do an air purge. That's a little bit optional. And then backwashing. Now, of course, the turbidity after that point we're not really tracking it. We're not producing any water. So As soon as we cut it off, we kind of recognize we're not paying attention to that line anymore. So past the cutoff, that line is imaginary, like what would have happened. So just keep that in mind. We'll cut it off. We're no longer monitoring turbidity because we're not producing water. If we had left it going, it would continue to increase. So with the air purge and backwash, those two processes, we flush out a bunch of water, we clean the filter, and then finally at the very end, we will say that's the end of the cycle. So we'll start with the ripening or rinsing. We'll produce some water, we'll stop, and then we'll clean it up, and that's the end of one cycle. We'll start again. Okay? So that kind of order of operations is something we need to keep in mind because each component is going to take some time. Most of the components will take some water or produce some water, and we need to be able to manage all of those given some amount of filters we have or some filtration area to understand where all that's going. Forgot that I gave myself a little extra room here, so I'll just write it out a little cleaner. So if we start here, and a typical head loss might look something like this. And I think I did turbidity last time. Sorry, let me. So this time we were looking at turbidity, and we see it. We have a lot of turbidity during rinsing. If we look at it from a different angle from head loss, we could do the same thing where we have a cutoff, but here it's going to act a little different because as soon as we clean the filter, it's easy to flow water through. So we're actually going to start on the head loss, on the pressure side. This will just simply look like this. As particles accumulate, we will eventually raise up to the pressure where we know that we're starting to risk water pushing through and channeling, and bad stuff happens when we over-pressurize it. So we will have some automatic cutoff there and maybe some preliminary cycle end if we're doing a time frame. Not cycle end, sorry. Filtration end. Actually, what I'm going to do is I'm going to draw this down here. Okay, so if we start here, then we have ripening or rinsing. Here, we would have production or filtration. Then we'll have maybe an air purge. And regardless, we will have backwashing. And one other thing I'll do for you here is I'll give you typical time frames. So we said production would be, I don't know, anywhere from 24 to 100 hours, something like that. The rinsing and ripening, this is probably 15 to 20 minutes. Okay, this does not take a long time, so it's not really drawn to scale. The air purge would probably be 5 to 10 minutes, just bubbling some air through. And the backwashing should also only take something like 10 to 15 minutes. So in total, most of the time for each cycle will be filtration. And as you can see, if we have a longer cycle time, we're producing much more water than we're using for backwashing. If we had to backwash every hour, a lot of the water that we're producing is going to be used in the backwashing, and in total, we're not getting a lot of water. Yeah?
So the horizontal line, is that for just water, there's nothing inside of it?
That's just a timeline. Oh, sorry, down here?
No, the red horizontal.
Oh, the red, yeah, sorry. That is a head loss limit. So we'll just call it a pressure limit. So if we had some cutoff, value that we said, at this value, we are no longer going to filter because we are risking the process. Once our actual head loss reaches that, we're going to stop.
Right, because I guess at the highest head loss, there's more particles that are blocking the water from coming through, so it's lower. So the higher the head loss, the lower the pressure, or the more of a drop in pressure, I guess.
Yeah, so the head loss is a drop in pressure. So if head loss increases, that means it's taking more pressure to flow through it. So to push the water through. And actually, this is a very important thing that I should explain better. When we're talking about head loss, we typically describe it this way because it's very convenient. We talk about hydraulic head in terms of the amount of the height of water or some liquid, because that height is essentially some potential energy, right? It is an amount of pressure. If you stack up a very tall body of water, that's a lot of pressure it's exerting down just by the force of gravity, right? And so if you stack up more and more water on top of your filter, the gravity's causing the push through it, but it's going to be higher pressure the higher it gets. So in these filters, we actually let them automatically readjust their own pressure just simply by gravity. So if the flow rate slows down a little bit, well, it's going to have more water loaded onto it, so the height will increase and it will match the flow rate. So we can feed the filters at the same rate, let's say some number of cubic meters per second. Well, the filter gets clogged, and so it takes more pressure, but it's automatically rebalancing because there'll just be more water sitting on top of the filter. So, and that's why we describe it as a head loss. So when we start filtration, let's say we have our filter bed here. Early on, we might have this much head loss or pressure or height of the water, but then over time, it will go up and up and up.
And the water level is getting higher because it's having a harder time getting through the granular bed.
Exactly. So the resistance caused by the particles getting stuck in the media makes it harder for water to pass through, meaning it's resisting that pressure, meaning the water level will rise accordingly. So that's a really good question there, because it's an important concept. This is how we operate the filters, and at some point, if we designed it poorly and we put too much pressure, eventually it's just going to push apart the sand and say, I'm just going to go through. The sand itself will be too unstable structurally, will part, and you'll get all your water flushing through with no treatment. Probably the opposite of treatment now that it's had already collected some particles. Okay, does that make sense? All right, so just keep in mind that it's kind of the vocabulary. If you get the vocabulary and you understand the cycle, you will probably have a good time, no big issues with this section of the course, because it's kind of word problems from there. I've got a couple of example videos, and maybe we'll start on some of the calculations as well. But let's get to the videos, because it's kind of neat to see them in action. I'm going to skip through them a little bit. I'll let you experience them a bit. I don't know if I'm actually allowed to share these. I'm assuming that it's going to be all right. Live, that is. For educational purposes here. So I'm going to get the sound working before I start this. Sounds not too important, and I'm going to mute it anyway when they do this air purge, but it'll give you a feel for kind of what's going on. Do this one. All right, so as you can see, essentially what's going on is they just start the air purge. So this is a filter that's dirty. It's been treating for a while. It's got these trough things, and they're just pushing air up through underneath it. And that's going to go on for a few minutes. This particular video lasts 6 minutes. So that's going to go on for a couple minutes. It'll continue. And eventually, they'll be done with that part, and they will then have to purge the air out of the pipes that they were just using. Here's where I'm going to mute it because it becomes extremely high-pitched and loud. Did you want to experience it? So, watch your ears if you come back and rewatch this at any point. So then they're going to stop the bubbling, to get the water out of the system. You know, I'm just going to put these. And then they're going to start flowing the water back through it. Probably be a moment later here. And you'll notice as soon as they do, let's see. Oh, still squeaking. Okay, so at this point, they're just starting to, or they're about to maybe, start sending water backwards through it. And it's going to do a little time-lapse thing for you. And you'll kind of see what's happening. There's still probably a lot of air bubbles trapped in the granular media. Okay, so it took some time. So grossly satisfying, right? I don't know if you heard it. I think somebody in this video is like, that's how they make root beer. And so you can see now how these troughs are kind of acting as a way to catch the water, distribute it into this main channel. And so this will then go on for some time. I have a second video that's nice because you can see after some time, you can then start seeing the filter bed itself and see how clear the water has gotten after some backwashing. So that'll be the next piece here. So I'll definitely be skipping through this one. At the start here, you see it's a filter bed, and maybe you can see a bit of different coloration back there. Here they don't have exactly the same troughs, but they do have sort of this little central trough and ridges to let water a little more smoothly cross, I guess. I don't think there's much interesting sound-wise in this one. Okay, so they started pushing water backwards through it, so you can already kind of start seeing some color changes as soon as they begin, which maybe they didn't yet. Here we go. You can see immediately everything starts looking a little different. You can see even the color, right? It's a very different color than last time. Okay, so we got the air purge happening. That'll go on for a little while. I think they've stopped the air purge by now, and they are starting to the backwash itself. And then you have that moment where it's overtopping. So this one's not exactly the same color, but it's same process, right? And then that'll continue for some time. And what's neat is you can kind of start seeing little pockets of water that just doesn't have nearly as many particles. So as we jump through it a little bit, you can kind of see it's getting clearer and clearer. Still some particles coming out, but you're able to then see through, and I guess the media itself is probably kind of a dark color. Nice little pan out to see the other filters that are in operation. And normally, if they're in operation, you see this one up here. This is just what it would look like. You've got water coming in through that middle channel and stacking up on top of these filters and letting water pass down through the filter continuously, and you're not really seeing a whole lot. It just looks like a flat thing of water. But underneath, we've got this stuff. Water is being injected in, and then it's just simply pushed through these filters over time. So this goes on a little while longer, cleaner and cleaner, until it's pretty much done. And what you see is it's actually starting to fill up because they stopped the outlet for the backwash. And right about now, they might be starting the inflow of their source water that they're going to treat. So then it's just going to stack up and be pushing as soon as they open up the valves underneath the filters. Then water will now be flowing from the top down through the filters instead of up through them, right? So hopefully that's a nice visual aid to what we're talking about with these granular filters. And hopefully YouTube doesn't fuss at me for using someone else's video in this manner. Okay, so I wanted to show you that. I think we'll just leave the equations for next time. It's really not super complicated. We'll talk about how much volume we're getting, how much volume we're using, and how do we time that when we need to do some kind of assessment for how many filters does our plant require. So, a little shorter today. We'll see you on Thursday.